Okay, it just happens, right? And you can't change its rate. So you can't change the probability or rate by any means. So it doesn't matter. You can't heat it up. It won't make it go faster. You can't smash it with a hammer. It won't go faster. You can't break it up into small pieces. It won't go faster. You can't do a chemical reaction. It won't go faster, right? It's something completely different. And obviously we know from the year 12 particle stuff, it's to do with the weak force in the nucleus. So it's completely separate from anything physical or chemical. So the experiment that we would have done would be throws of dice. And obviously we're modeling here time. And then we've got number of dice remaining. And we're modeling, obviously, the number of nuclei remaining. And if you do that, you get this lovely curve like this. Okay. Obviously, the individual data points might be like this, but the curve is smooth. And the point of this is to obviously show you that the decay, the probability of decay follows this nice pattern. And if we start at the top with 100%, or it might be 100 dice or 50 dice, then we get this constant property, which is the half-life. And if you halve it again, so that would be 50%. If we halve it again, it's 25%. Again, we get this constant property of the half-life, right, which is a nice quirk of this mathematical relationship. Okay. So you can do this with number of nuclei. You can do it with the mass, or you could do it with the activity. And we'll talk about what activity means in a second. We need to define half-life, which I'm sure you all know from GCSE. The definition hasn't changed. The time it takes for half the atoms in a sample to decay. Or we could equally say the time it takes for the activity to halve. So what do we mean by activity? What we simply mean it's the number of decays per second, and it has its units are, it could be per second, that's perfectly fine, but we also call it a becquerel. Right, and as you know, right, this unit per second, I mean, there's loads of different ways of saying per second. We can say per second, we can say hertz. Hertz means per second, but that's specifically frequency. We can say becquerel, but this is specifically radiation. And I think the reason these have different units is just to link it clearly to the topic that's involved. But you can say per second.
So,
hi, Abdallah.
What does it say at the top next to radioactive decay?
It's because of the weak force. So it's due to the weak force.
Oh, it says weak force. Okay.
Yeah, that was just, yeah, like a reminder. So let's start to do some more advanced maths. Right. The activity of a sample. Right, how can we calculate it? Well, it's quite simple. We calculate it like this. And I'll write what I mean by these words. So the activity, which is the number of decays per second, is equal to the number of nuclei or dice multiplied by the probability of decay. So lambda here is this thing called the decay constant, where it's the probability of decay. So if we were doing this with dice, then obviously this would be a 6. If we were doing this with coins, and you get exactly the same graph if you do this with coins, then lambda will be a half. If you did this with a 20-sided dice, then this would be 1/20th. Okay. Each isotope has its own value of lambda. Okay, so this is unique to each isotope. And obviously, the larger this number is, the greater the decay will be, the greater number of decays, and therefore the smaller the half-life will be. If this is a really small number, then it's not very radioactive and the thing will last for a very long time. Now, there's one thing I'm missing out from this. Right, obviously, this is a relationship that's always going down. The number of atoms is always decreasing. So what I need to do is just put a minus sign in here to show that the whole thing is decreasing. The units of this are per second because this is just a number. So obviously to match the units of activity, the probability of decay has to be per second. Now, there's a slightly more formal definition of the decay constant. Probability of decay is fine, but often it's defined as the fraction of the total number of nuclei present that decays per unit time, assuming time is small. This is just a very long and tedious way of saying probability of decay, right? You can obviously, think to yourself they mean the same thing. Right, are there any questions at this stage? Okay, so let's carry on. So activity is minus lambda m, same as what we've just said. Now, activity is the number of decays per second. So how can we write number of decays per second? Well, we could say it's the change in the number of nuclei in some time. Okay. So number of decays per second. You might be able to see where I'm about to go with this. Okay. What happens if we make this time interval very, very small? Right, what happens if the time of interval approaches 0? Then we can write down a mathematical expression like this: dn dt equals minus lambda n. And now what can we do? We can solve this using calculus and obtain a nice expression. So in fact, yeah, I'll give you 2 minutes to solve this for n. So I want an expression for n equals something.
Wait, what did you ask for?
Right, how are we doing? Have we managed to solve it?
No, I haven't.
Have you forgotten your maths?
So I can hear what you said. What are we solving?
Oh, we're going to integrate this equation to get an expression for n. Who's your maths teacher? They're going to be so sad. So what do we need to do? We can't integrate like this. We need to make sure that we have all the n's on one side and the t's on the other. So we can say dn is minus lambda n dt. Now we can't integrate the number of nucleus with respect to time because doesn't make sense. So we need to put the n on the other side. So 1 over n equals minus lambda dt. So I've forgotten the dm. All right, so now I've got some expression of n with respect to n and some expression over here. This is a constant, this is just a number, right? And we can integrate a number with respect to time. So let's integrate both sides.
I think this is A2 integration. I don't think we've done it yet.
Okay. That does surprise me, but then maybe I am a bit out of touch with the math syllabus. Never mind, we'll go over it anyway. I will just say this is obviously not, you wouldn't be expected to do this on an A-level exam, but I think it's nice for you to see this because it links with maths. So what have you integrated so far? Have you just been integrating simple expressions like x to the n or sine theta?
We haven't done integrating sign.
I think we've only had, most classes haven't done sine yet even, but I think like couple classes have.
Oh, okay. So
We haven't even started it yet.
oh right, okay. because like, it's really, I mean, there's a proof of it, which I'm not going to go into, but the results are really easy, right? If you differentiate sine, you get cos. If you differentiate cos, you get negative sine. If you differentiate negative sine, you get negative cos. And then if you differentiate it again, you get sine. So if you integrate it, you go this way around. So it's really easy to remember. The reason I mention this is just because when you're looking at simple harmonic motion, right, often you start with sine for maybe like displacement, and then velocity will be cos, and then acceleration will be negative sine, right? So what's the relationship between displacement, velocity, and acceleration? Obviously, we know that we're differentiating. And if we go the other way, what happens? We're obviously integrating. So there's just lots of nice links between this. Okay, so maybe you haven't solved this. So let's carry on. So we've got our variables over one side. So now we can sum up both sides. This obviously just means summing up. So if you to integrate 1 over n, you'll just have to believe me that you get ln of n, right? The natural logarithm. And if you differentiate the natural logarithm, you get 1 over n. Well, I'm not going to prove that, but that is the result. And then if we integrate this side, we get minus lambda t. But there's something missing. We also need some constant as well, right? We need the constant of integration, because if you differentiate this, you obviously get minus lambda, but then this constant disappears. So you need to replace the constant, which may or may not be there. It could be 0, but we need to allow it to be there. So now we need to solve this for n. So if we put both sides to the power of e, okay, then what is e to the power of ln of n equal to? That's just equal to n. And then the other side, obviously, that is just equal to minus this. But we can simplify this slightly. If you know your powers, you can say that's equal to e to the c multiplied by e to the minus lambda t, because obviously if you multiply two things together, you would add the indices. And then this here, we change this into something that's a bit more useful, and we replace this with a constant, which we say is n naught, where n naught equals the starting number of nuclei. So we've got an expression for how many nuclei there are as a function of time. And we got that from purely saying that the rate of change of nuclei, or the activity of the nuclei, is just simply equal to this really, really simple mathematical expression, right? The probability of decay times by the amount of nuclei, right? This might be stating the obvious, but just think about the dice example again. If we had like 1,200 dice, the probability of a dice rolling a 6 and therefore being radioactive would be a 6th. So we're obviously going to have a change of 200 dice. If we then have 1,000 dice, the probability of decay is a 6th. We're going to have about 150 or 160. So again, the activity or the change is 150. Okay, and now we're just generalizing it to this point here. So obviously this you don't need to know, but I think it is nice for you to see that where it comes from. It's not actually that hard if you've done integration. So this expression is important, but there are alternative forms, right? We could write it in terms of mass, because that will follow exactly the same pattern, and again it comes from the same maths. Or we could do it in terms of the activity. Again, it will follow exactly the same maths. Just like if we think about capacitors, what do we know? We know that V is V naught e to the minus t over RC. We know that Q is Q naught e to the minus t over RC. And we know that I is Q naught e to the minus T over RC, or maybe it's plus, depending on what we're looking at. Okay. Are there any questions so far? Right, you might have noticed a slight difference. If we look at the capacitor equation here and we compare it to this equation here, what do you notice? Here it's T divided by RC, and RC is just a time constant. Here it's lambda times T. So the reason for this difference, right, is because RC has the unit seconds, so time over RC has no units because it's seconds over seconds. Here we've got time, lambda has the units per second, so per second times by seconds equals no units. And you can never have units in an exponential, just like you can never have units in a sine or a cosine. Right, just a little bit more, and then I've almost finished with the maths today. So let's start again with this equation. So supposing we make it look like this. Okay, so the number of nuclei divided by n naught. So this is obviously the fraction of nuclei left, right? Because this is the starting number, and this is how many are left. So what happens if we set this to a half? Okay, then what are we really doing? We're really now saying this is the half life. So when this is equal to half, it's going to be equal to this special time called the half life. So now we can solve this. Ln of a half is ln of e to the minus lambda t a half, which is obviously minus lambda t to the half. So now let's quickly rearrange that. T to the half equals ln of a half over the decay constant, or a negative decay constant. And if we type that into our calculator, we get minus 0.693 over lambda, or if we get rid of the minus signs, this. So we've got an expression for half-life here. Okay. It's given as a number on your formula sheet, but it's useful to remember it is actually just ln of a half. And there is a difference here with capacitors. Because with capacitors, we're always looking at a time constant. And what does one time constant equal in a capacitor? It's the time to fall by 67%. But with radiation, we're always looking at the half-life, the time it takes to divide by half. So there is a difference here. I don't know why, other than it's just kind of convention. Right, you could equally work out a half time. I think to explain the convention a little bit, if you think about the capacitor equation, right, what we do here is we're very much saying when T equals the time constant, when T equals RC, and because of that, it leads to this. But here, it doesn't necessarily make the same sense to say when this is equal to this, right? Because they're multiplied together. So that's why we talk about a half-life, because it's a convenient fraction rather than this 67%. So it does make sense where it comes from, but it also, to some extent, it's not important. Right, I'm just going to ask a quick question of all of you with my new favorite function in the Google Classroom, is a quick poll. I know I could ask you because there's only 5 of you, but if you could just select one of the options, please. I think you might need to go into the chat to do this. All right, we're split. All right, we're split. So if you want to do questions, please do just get started with the questions. There are 2 sets in the lesson. There are radioactive decay questions 1, which are more on half-life, and then there's the radioactive decay questions 2, which involve this a lot more. If you want to get on with those, please do that. You can just mute me. If you want me to go over a worked example, I will go over a worked example with you. Let me just find a suitable one. Okay, we'll work through this question here. So I'm just going to quickly make a note of it on a bit of paper because I don't think it's. I don't know if you can see both the PowerPoint and my piece of paper. Okay. So we'll do this question. So the full question is: a radiographer has calculated that patients to be injected with 1 × 10⁻¹8 atoms of iodine to monitor thyroid activity. The half-life is 8 days. Part A says calculate the decay constant. So things you need to have in mind is the activity is minus the decay constant times the number of nuclei. The half-life is 0.693 over the decay constant, and the number of nuclei is the initial number times by e to the minus decay constant times by time. So if you always have those 3 in mind, you can pretty quickly get to the one you need. So the decay constant, how many atoms will decay? Well, we can work that out by looking at the half-life. The half-life tells us the rate at which it is decaying, basically. If it's a short half-life, it decays quickly. A long half-life, it decays slowly. So for part A, the decay constant is 0.693 over the half-life, which is 8 days. Now, we obviously need this to be in seconds because everything so far has been worked out in seconds. So that's 8 times 24 times 60 times 60. Which is 1 times 10⁻⁶ per second. That doesn't seem right. I feel like I've made a mistake here. Maybe not. Right. Right, the initial activity. So the activity is obviously given by the number of decay, or the probability of decay, times by the number of nuclei. So if we know what the decay constant is, and we know how many atoms there are initially, we can work out how many decays there will be at the start, which means there'll be 1 times 10 to the 12 decays per second at the start. Part C, how many undecayed atoms are there after 24 days? So there's two ways to do this. We could use this equation, plug in 24 days, work out n, or we could spot relatively quickly that the half-life is 8 days, and this therefore is 3 half-lives. So if we start with 1 times 10 to the 18, that's going to be divided by 2 to the power of 3, because we halve it again, halve it again. Which means there will be 1.25 times 10 to the 17 atoms after 24 days. Part D, the total activity after 3 days. So now we've got the activity is still our decay constant times by the number of nuclei. We've got 1.25 times 10 to the 17 nuclei after 3 days. Decay constant is the same. So we've got 1.25 times 10 to the 11 becquerels or per second, decays per second. So it just goes to show you that sometimes these numbers are not necessarily what you expect, because to me that seems wrong, but I don't think it is wrong. I mean, we followed the rules, followed the maths. I can't spot an error. So these numbers might make you think twice.
So can you move this sheet a little bit down, please?
Right, we'll do one more example. So I'll post it in the chat and just give you 30 seconds to read over it. Right, so there's two ways to do this question again. Right, there's the longer way where we could use this, and we could say that lambda is 0.693 over half-life. So we could say m is m0 e to the minus 0.693 over the half-life times by the time. And then we could plug in our numbers of 2.4 minutes converted into seconds, 7.2 minutes converted into seconds, and 100 grams in here. That would be fine. That would give you the correct answer. Sometimes you would need to use this, particularly if the numbers are not very nice. If the multiple of this is not very nice, then you'll need to use this. But in this example, we see that we have 100 grams at T0. At 1 half-life, we're obviously going to have 50 grams. At 2 half-lives, we're obviously going to have 25 grams. So this is going to be 0 minutes, 2.4 minutes, 4.8, and then 7.2 minutes is going to be 3 half-lives, which will be 12.5 grams. Right, so maybe I should have picked a harder question, but maybe we could convince ourselves this gives us the same answer. So 100 grams times by e to the minus 0.693, and then 7.2 over 2.4. Now, I don't actually need to convert to seconds here because this is minutes divided by minutes. So all the conversion factors will cancel out. So there we go. We get exactly the same answer if we type it in to the calculator. I don't know if you can see that with the shadows.